Refrigerant recovery is the foundation for life cycle refrigerant management, as without safe refrigerant recovery, there cannot be reclamation or reuse. A-Gas Rapid Recovery is an on-site refrigerant recovery service that gives businesses an easy way to contain their used refrigerants.
Not a whole lot of companies do what we do. We handle some of the grunt work that they don't want to do, and we can do it 10 times as fast as they can. The recovery portion, cylinder exchanges, and buying back used material that otherwise can't be used.
We play a big role with our contractors, whether that be HVAC, mechanical, or demolition contractors. Our whole purpose is to get on site and not only help them save money in the project, but offer an environmental solution.
We do not want any of these products getting vented to atmosphere, no matter how low the GWP is. Now it's not only the cylinder to recover the product, but it's making sure the technicians have equipment that are rated to work with flammable gases. That's really important for people.
So by us being able to contain it in the cylinders, reclaim it, we're saving the environment one recovery at a time.
My name is Mike Idle. Today I wanted to give you an overview of Amatrol's T7300 HVAC control system. This system is designed to align a hands-on workstation, as you see here, along with interactive curriculum to teach the operation, installation, application, and troubleshooting of control systems related to the HVAC industry. As components and features of HVAC systems get smarter in both the residential and commercial fields, it's important for current and future HVAC technicians to be trained up. What types of circuits are used, familiarity, learning, operation, maintenance, troubleshooting are all important areas to cover in that.
Here at NAVAC, we are obsessed with delivering the best HVAC tools on the market. Our tools are built for professionals and engineered for precision, just like Harley-Davidson motorcycles. NAVAC Nation, it's time for you to feel the power both on and off the job site. Let's stand up in our pursuit of perfection. From coast to coast, NAVAC forges the path forward. Wherever you are, we will be right beside you.
Hello, everyone. Thank you so much for joining us on Did You Know, the ESCO HVAC show. We actually have a party going on today. We are hanging out at the Johnstone Supply Indy West. They have a leadership educational conference going on this week. And Tom has been hanging out with Aaron here doing some of the leadership education along the way. And now Zoom is going nuts already, isn't it? I think that's a hand gesture that one goes to. I'll actually skim that back over. That's the beauty about having these cameras. We do. Oh, it really likes you. So we're going to spend a little bit of time diving deeper into thermoelectric motors. And I wanted a couple of things today. I wanted to make sure we had a proper introduction to Jocelyn, who joined our team it's been almost 2 months already, hasn't it? All right, hold on. Let me make sure to get that one. You should have a feed now. So, Jocelyn, do you mind introducing yourself to the industry?
Yeah. Hi, I'm Jocelyn. I just turned 24 in September. But yeah, have a marketing background. HVAC is very, very new to me. So it's exciting because I just wanted to learn something new, try something new. Marketing can get very bland and boring with the routine posting, and this is taking me out of my element. So I'm really excited. Yeah.
It'll definitely take you out of the element. Everyone in this industry knows that, like most of us end up here, not exactly planned on getting here, but we do enjoy what we work on. And it was really enlightening. We were walking by one of the tables. We're actually going to see it here in a little bit. And Jocelyn says, "What are these?" And they're meters. She's like, "What do they do?" do. I don't like not knowing. I'm like, yes, you're going to fit in right. I know. Kendrick, thank you much for joining us in Chicago. Everyone let us know. Oh, Jason O's joining us today. Hey, man, we are so glad to have you here with us, bro. Yeah, everyone let us know where you're joining from. We are in Indianapolis, Indiana. We're on the west side right now. And I think before we get going, I want Aaron to share a little bit with us about the program that he has going on here this week.
Hey, thank you. So, we had Tom out this week. It was week 2 of a program called Foundations of Leadership. You've got a really nice toolbox here behind us. And so we were loading up a toolbox of a different type this week. We're loading up the people skills toolbox. And so, as you know, from teaching generations, we have a duty in this industry to prepare the next generation, as every industry does. However, what we found, though, is that there's a gap now because of these things in communication skills and conflict de-escalation, and understanding each other, and really just seeing people as people. And so we did some work on that this week. Tom is here. He has his own perspective, so I'll let him speak for himself. But it was a really, really good week, and we just wrapped it up today.
So Aaron is an excellent mentor. He's given people skills by sharing his own life experience. And the Foundations of Leadership class gives people the opportunity to find in themselves what they need to succeed, to make changes in how they work with people, and to see the world from a new perspective because of their own choices, not because somebody's telling them to be different.
Love it. Love it. Excited to learn a lot more about that. Encourage all of you to go check it out. Aaron, the YouTube channel is
Foundations of Leadership 3438.
Excellent. All right. So we are going to have some fun today talking about a topic that I was telling Jocelyn, I really didn't even know enough about myself just a couple of weeks ago. So I've been working on building this barn dominium out. It's been kicking my butt, but getting closer. So got the wood fireplace put in a few weeks ago. And someone was telling me about the electricity-less fan. And I went, okay, what are you talking about? And they're going, I don't know, it's some kind of a thermoelectric thing for a wood burner. And I went, okay, yeah, I kind of have heard about those before. Now I need to learn a little bit about it. And so I did a little social post on how it worked, and it was really had a lot. Actually, let me see. I think I've actually got a short video pulled up from, so check this out. Right, so there's the fireplace, and there's the fan operating with no electricity whatsoever. So it's a thermoelectric device. And I wanted to get one to see how it worked, and it actually worked even better than I was anticipating. So I wanted to do a little bit of education on what it was. And some of that took me doing research to be able to understand exactly what that was. So a lot to it. Now, let's look at, that's the wrong presentation. Hold on. Let me get rid of this real quick because we're going to do some hands-on demonstration as well, which is going to be really cool. No, I don't want that one either. Let me fresh one. Let me add a new presentation. Sorry about that. Should have already had that thing fired up. Okay, so we're going to spend some time learning about thermoelectricity. And along the way, we're going to understand how it offers a variety of different solutions in some really, really cool training opportunities in the classroom. So let's look at thermoelectricity real quick. Let's look at how we're producing electricity from heat. It's a really intriguing concept. And I have spent time years ago, actually high school and into college, working with electricity and electronics. And so I remember diving into, the understanding of semiconductors, didn't really understand all of the different applications that they provided. When we start looking at semiconductors, we're talking about material that is not really a conductor, not really an insulator. They fall in between. And there are certain types that are more of an insulator. Imagine an insulator that has holes in it that allows things to pass through. So when we take different semiconductors and we start putting them into a circuit and we introduce a change of temperature across them, the change in temperature actually creates a change in electron movement. It gets the electrons flowing, which, as we know, when we start flowing electrons, we're going to start moving electricity. So the semiconductors are built on the principle of using a conductive material of some type as one surface layer. And then we're going to stagger semiconductors N type and P type. Now, if you're interested in doing a deep dive into semiconductors, I think I should bring in Professor Silberstein. That is really his world. So let me know in the chat if you think that we really need to do an entire class on semiconductors and how they work, because it was intriguing. And by doing this research, it really refreshed my memory on how semiconductors work. Anyhow, so we're going to use a type of material. We're going to use our semiconductors placed next to each other to create a circuit. We're going to be creating a series circuit. And then we're going to use a dissimilar metal on the opposite side of that. And a lot of times we're going to have a ceramic substrate, some additional type of layer to break the conductivity. Now, what happens in that process? We're using these two different types of semiconductors. If we look at that N type of semiconductor, we typically use those for faster moving. Most of those are based with some type of a phosphorus or arsenic or antimony. The thing about them is they have plates. Like they're more solid, but they have holes in them. And then when we look at like the P type semiconductors, they move slower. A lot of them are based with like boron or indium or gallium. And when we use those next to each other, I think it is. I think it'd be a good class for us to introduce like how semiconductors function. Because I'm telling you, when you hang in to the end of this class, I'm actually going to show you and spark a whole new conversation on how we use N-type and P-type semiconductors for solar panels. This entire project that we're in is being powered right now by solar panels. So this whole thing is running, the studio is running off grid. And thank you so much to our sponsors. Our sponsors have given us the opportunity to just be creative in the way that we build out this studio. Now, let's look at this arrangement of our semiconductors. How we produce electricity from temperature has to do with the way heat transfers across the combination of these semiconductors. Okay, I think we're going to do it then. We really appreciate that. Yeah, definitely let us know. We'll make sure that we build that. And any other type of topics that you want to cover. Now, look at this. Look at this electrical circuit that we're building using our semiconductors. We take our N type. See how we're doing a series chain from N to P, from P to N to P. We're actually creating a circuit out of these semiconductors. Now, if we put a temperature change across that, we put a temperature differential across those dissimilar plates that are on each side of our semiconductors, it causes the heat is going to transfer through those semiconductors. As it does, it gets the electrons excited and we start producing voltage. And we can actually use those to move devices. That's what we're going to do. I got an entire demo set up for us. We're going to move over there here in just a minute and do some of these hands-on. Now, it comes back to some principles that we work with in our education when we're talking about principles, right? When we're doing our curriculum studies and we're learning about electricity, a lot of times we'll hear about the Seebeck effect. I'd heard it, didn't really understand it well until I started diving into the research. And then I was like, well, this is very fascinating. So the Seebeck effect really is that process, right? When we have dissimilar metals, it's hot on one side, it's cool on the other. The temperature differential gets those electrons moving, and it allows us to be able to move electricity. So there's a variety of different materials we can use. This particular one is actually showing us chromel and alumel. Ooh, Murph, you're going to like this. And because it's exactly why we're having this conversation. Have you ever thought about a thermocouple? Now remember, we still have thermocouples out there that we work on all the time. How they actually work? How do they tell the furnace that we have flame? Well, this is actually a thermocouple. So Real Pars is a thermocouple manufacturer, and this is exactly how they do that. That thermocouple sitting in the flame of the furnace, particularly on a pilot assembly, is going to excite the electrons enough to produce a very small millivolt DC signal that we can use to hold in contacts on a gas valve or tell a board that, yes, we actually do have flame there. And that's the technology that we had used in furnaces for decades until we went to solid state electronics and we went to a flame rod. Whole nother class. We got a wonderful episode on what happens in that circuit. Yeah, and Jason O, the thermopile is thermocouples tied into series. When we go back and we look at that N to P type semiconductor, those are just running in series and they're DC voltage. So if we put additional ones in series, it will increase our voltage, which is how we get a thermal pile. It's a pile of thermocouples. Now, there is another effect that's very similar to that, and it's called the and you can pronounce this, depends on where you're from. Here in the United States, we're probably going to call that, how would you pronounce that? Peltier, maybe? I would say, get up to our Canadian friends, they're probably going to say it's Peltier. But if you look at that exact same representation, what would happen if I applied DC voltage to that same circuit? Remember, we've done quite a few classes talking about how a motor is a generator. Well, if we look at this same principle, if we apply power to this same device, the same semiconductor plate, it actually will excite the electrons to the point that we actually move heat with our electrons. So as our electrons are flowing through the plate, our temperature is moving correspondingly with it between the dissimilar metals. And that's where the Peltier effect comes into play. So they really are just opposing views of the same type of process. Actually, Peltier did his studies on Seebeck's effect. Now, let's move forward a little bit. Let's put that principle into play with this thermoelectric fan. Well, the fan, it sits on top of a stove, right? A wood stove, a hot surface. And then it dissipates heat through it. There's a temperature differential. And in that, we produce electricity. Want to go see how one works? What do you think? All right. Okay. So I've got more slides. I'll come back to them. We're going to go do a little bit of testing, and then we'll come back and spend some more time into the slides. So I think what we're going to do now is I'm going to bring in the secondary set of cameras. Let me just change camera views altogether, and we will bring in, let's bring in this one. Okay. Sound good?
Yes, it is.
All right. And I am going to switch from this main microphone, bring in our wireless mics. How are they doing? Everyone in the audience, our microphones coming through okay for you? And just let us know in the chat. All right. I'm going to head on over, Jocelyn.
Okay.
What do you think? Are we doing all right?
Yeah.
Okay.
Looks good.
So let's take that fan that we were just talking about, right? So here is our heat transferring fan. And if we look at the construction of it, what are we doing? We're using a base that is going to be a heat sink. So the base is going to absorb temperature from the hot surface. And then we're going to introduce one of our, they typically get called Peltier plates, but it's that whole same principle, that Seebeck Peltier effect. We're going to introduce one of our semiconductor plates in between. And our semiconductor plate is going to be connected to another heat sink, which is going to be another dissimilar metal, which are these additional fans here on top. So what we're going to do is we're going to apply heat to the base. The base is going to be warmer than the top. And as the heat passes through our Peltier plate, it's going to get the electrons excited. It's going to produce electricity, and we're going to power this little bitty DC motor. So we're going to do two things here. We're going to monitor two separate things. We're going to got a few meters going on just so we can show you different aspects here. Now, we are talking about DC, so we're going to put our meter on DC. So with this meter, we're going to be measuring voltage. And there is a tad bit of voltage coming off from this Peltier plate right now. It's not much, 0.1 to 0.6, depends on when the sun hits it. It's actually going to produce a little bit of DC voltage. So we will monitor the DC voltage there. This one, we're going to do something different. This one, we're going to monitor temperatures. So we're using two K-type thermocouples, one that is attached directly to the base. So we're going to be monitoring the temperature of the base. The other one is here on the back side, and I've set it into a little screw mounting hole so that we can measure the temperature of this heat sink. So it's really what we're doing. We're measuring the hot heat sink and the cooling heat sink. This one here is going to dissipate heat into the room, so it's going to be closer to room temperature. This is going to be our heat one. This is our little electric Bunsen burner heater, which I absolutely love. If you haven't seen the fractionation video, it's really cool. It's the same thing. We're using the same heater. So what we're going to do, we're going to go ahead and introduce heat into this. I'm going to walk on the other side so I can show you the meters here. So what we're going to see, let me make sure this is in here well, right into the middle of the heat stream, because most of the heat is on the middle of this pad. So what we're going to see in our DC voltage, look, we're already starting to show some things, right? We're starting to see a variation in voltages. That's because our temperature is rising. So if we look, our bottom temperature, can that be seen in the video, Jocelyn? Mm-hmm. 122? Excellent. So our base temperature, our heated temperature, it's 131 right now. Our secondary fins, we're running 77, 78 degrees. So we're starting to get a temperature differential between our base plate and our upper. So what is happening is we're starting to produce a little bit of voltage off from, let me check my connections here real good. Yeah, that looks good. We're getting a little bit of temperature. Oh, there we go. It wasn't setting very well. We're starting to produce a little bit of temperature off from our Peltier plate. Earlier, I had a lot more heat than that. Let me make sure it's making contact. So we're at 206 on our base. We've got a change in temperature happening right now. And as you can see, we actually started moving just a little bit. Let's see, this thing was produced. I'm going to swap this out for a different one real quick, just in case it's not reading properly. So this is a higher current one. Oh, there we go. Now we're starting to produce. So we're actually producing a DC voltage. And if I get this one operating properly, we'll see what that DC voltage is. And based on which direction, there we go. Based on which direction will determine how much voltage we're actually putting out. So you'll see our voltage increasing. We're in millivolts right now, around 450 millivolts DC. And as our temperature increases, so does our voltage. And so you can actually see that we're starting to spin faster now because we have a larger differential across our Peltier plate. So at about 450 millivolt DC, we have enough to move this particular fan. So that principle goes into play for a variety of different applications. I can't wait to talk to you about how that actually works with solar here in a little while, because it's an intriguing concept. Yeah, I may have gotten that one too hot. That was one of the things that I found in the research, that the Peltier plates are limited in their operation because some of the semiconductors will overheat and not function properly. So we're typically limited to 350 to 400 degrees Fahrenheit. And so we're actually running We actually hit 380 a little minute ago. So I'm going to tone that back down a little bit. And then we'll work with another semiconductor here in a minute and show you what that one looks like. So in that, we can simply look at heat transfer being an effect on the flow of electrons that can generate a voltage. So it's an intriguing concept that's very inexpensive for us to introduce into the classroom. And when we can show that we're actually using these plates as conductors of temperature, this has become a heat sink. We've absorbed heat into this base plate. I'm still 337 degrees on that base plate. It's jumping around a little bit, probably because it's not making perfect contact. There we go, 330-ish. So I'm still 330 degrees, even though I have no heat being introduced to it. And so this thing's going to run for quite a few minutes. We'll let it go on its own. And as that differential between our bottom plate and top plate starts shrinking, so will the production of millivolt DC to our motor. Eventually, it's going to slow down. It's going to stop. But it actually moves a fair amount of air. It's very impressive to see how that operates. All right. So a very cool thing to introduce into the classroom, but there are a lot of other concepts that goes along with that, right? Let's go back and look at some of the presentations again. And you're welcome to hang out here.
Sure.
Yeah. So let's go up to our PowerPoint presentation. Let's change the video feed. Right. And we'll go, there you got it, to the OBS bot. And let's go up to scene number 3 on the top. That'll be our slide presentation. Or I guess it's the 4th one down. There we go. All right. So when we look at that thermoelectric effect, and we can turn a motor, well, what else can we do with that? Well, let's move on to the next slide and let's talk about that. When we start taking that principle and we apply it, we can start thinking about other applications that we could use that. What about for cooling? Because remember, if I use that in an opposing mode, I can actually move heat with electricity. Okay? So think about that. In this particular scenario, if I use the same device and I applied power to it, I could actually move temperature. I can move heat. So if you haven't seen a thermoelectric cooler yet, I encourage you to start looking a little closer at them. They don't have refrigerant in them. A lot of the small electric coolers that are both AC and DC powered, those are actually thermoelectric coolers using this exact same device. I have an example of one out of a cooler. I'll show you here in just a second. So that's what we do. We apply a DC voltage to that same plate, and then we turn some fans to move air, and we will transfer heat electrically, right? No refrigerant whatsoever. Let's go to the next slide. Now, this is what we're actually starting to see in the industry, which is why I wanted to do this class, to show you the things that we're starting to be introduced to that really need to be taught about in the classroom, because they are already out there. So this is a lab thermoelectric cooler. They're becoming very popular because they don't have to worry about refrigerants. Jason O's right here. He can tell you how difficult it is to get the approval for some of these new coolers that have A3 highly flammable refrigerants in them in sensitive areas like laboratories. So we can use thermoelectric cooling to produce the same effect, the removal of heat in a very controlled environment. And so we already have thermoelectric coolers out there. But think about the process. Jocelyn, if I could move heat from one side to the other, and I'm using DC power, what would happen if I reversed my DC power? Do you think I can move the heat the other direction?
No.
You actually can. And when we first think about that, it's like, how could we get so stuck on a refrigeration process of it goes one way. Mm-hmm. We move heat one way, right? I turn my air conditioner on, my heat goes outside. Well, with the thermoelectric, it's a complete different scenario because we are using electricity to move the heat. DC voltage, we can reverse the DC voltage. That's right, Jason O. His PC uses the same cooling method. That's why we're starting to see a lot of these products. They don't have refrigerant in them. Now, yep, you're right. Water coolers as well. So we would consider this a new technology a decade ago, but today it's technology we should be discussing and we should be teaching on. Because if I go to the next slide, I could take the exact same device and change the voltage on it or flip it 180 degrees. And now I have a thermoelectric heater. So for vaccines that require a high temperature, we're using this exact same idea because I don't want to introduce an A3 highly flammable refrigerant into a refrigeration cycle if I don't have to, if I have other solutions. And so the thermoelectric option is becoming extremely prevalent. Now, let's go ahead and move forward. So if we take that principle and we take our Peltier modules and we start stacking them on top of each other, or we start stacking them in series, we can actually increase that capacity. Takes more electricity, but moves more heat. That unit on the left, that is a commercial refrigeration unit.
So it's a heat pump with electricity.
It's a heat pump with electricity, Katie. You're exactly right. Without having to have that mechanical reversing valve in between, we are simply doing it with electricity. So you could have larger units, you can have smaller units, all running on this exact same principle, and we can have it in the classroom, and it's simply an electrical project. Now, let's go forward and look at what else we can do here. We are now producing commercial thermoelectric refrigeration units that are producing a lot of BTU movement. This particular one, now think about this, it's 20 inches wide, it's 34 inches tall, and it's 10 inches deep. About the size of a window air conditioner. Because this unit right here moves 5,500 BTUs. It's the same as a 5,000 or 6,000 BTU window air conditioner, and it's doing it completely electronically. We could call it electrical, but it's really electronic because of the semiconductors and the controlling device that it is using. It's only 10 inches thick, right? If we go forward again, we can start thinking about another application. So Jocelyn, if you can send that camera back over here, I want to talk about something else for a minute. Look, we're still running. We haven't had power on in quite a few minutes, but we still have enough of a temperature differential. Look at that. We have enough of a temperature differential that we are still running and still producing 31 millivolt DC. That's off that little guy. No, it's off the big one. Okay. Now, okay, so think about this. Those 12 volt / 120 volt coolers that we see, this is all that it is using. We're using heat transfer via temperature because of the air movement. So with this little unit operating at 12 volt DC, I can create a cooler or a heater. And we're going to show you how. And we're going to let that run. We can always put our temperature probes back in here in a little while. Right now, what I want to do is let's discuss the heat transfer of this. And I'm going to leave that one there. Let me move. This is our sponsor, NAVAC. I encourage all of you to learn more about NAVAC tools. We have a whole bunch of them we're going to be introducing to you here in the next few months. All right, let's take this device. So we're using copper because copper is a good dissipation tool of heat. So we're using aluminum fins to transfer heat into the copper tubing that we're running into our heat sink. We're going to use fans to move air across this heat sink. And then we're going to energize our Peltier plate. And then we're going to turn on a fan to move the heat that is being transferred across that Peltier plate. And we're going to monitor that because this is really an intriguing example. And it's so inexpensive. All of this stuff came from Amazon. I think we spent $45 on all of these, including a project to build your own Peltier plate. So we're going to put let me get it down inside to make sure we're getting good. We're going to put good to make sure we get good contact. We're going to put a temperature probe in this coil and in this one, and we'll let them stabilize a little bit. There we go. We're getting down into the 90s. Right. Now, we're going to energize all of the above. We're going to energize our fans, and we're going to energize our Peltier plate. And I'm going to have to move this around a little bit to be able to show voltage and to be able to connect the things. So hopefully you can see that well. We're going to shift that just a little bit. So we're going to be producing our millivolts DC across our Peltier. Or I'm sorry, we're going to be introducing voltage across our Peltier. We're going to apply 12 volt DC to our fan motors. And as you can already see, our temperature differential is starting to shift pretty rapidly. All because we have energized our Peltier plate and we have allowed heat to move relatively quickly across it because of our amount of airflow. So we have, in seconds, created a wow, I got to move here to see it. And that one's 110, that one's 99. Make sure that I get it down in the coil here. And that we're touching. Hang with me. I make sure our thermistor is here in the right location. I had it down to 32 degrees earlier. In no time flat. But it's got to make connection on our surface. I should have put a clamp style on that. All right, give me just a second. T1's having a heyday.
Scott V asks, just got home, what did I miss?
Do what?
He said, what did I miss?
Oh, you missed a whole lot. Right now, we're creating a cooler. Oh, yeah. Boy, let me find the right place for that temperature probe because I really want you to see where we're at here. Unless my temperature probe is off. It did get pretty toasty a while ago. There we go. So right now we are running a 52 degree evaporator and an 87 degree condenser, all off from electrical flow. Now I let this run a little bit longer, watch you get down into the 30s, and I am moving air across it. So it's not a stagnant evaporator. This actually is an air over evaporator. So simply by energizing our Peltier plate, getting the electrons flowing through our semiconductors, the heat is following the same travel as our electrons. And so we're able to move the heat from one area to the other. No refrigerant whatsoever. Simple heat transfer. And so it's an incredibly interesting project to bring into the classroom to show how we can do two things. We can move heat with electricity, or we can produce electricity with heat. And in the kit, what you'll find, very simple. We'll have a base control. This particular one is just a standard solder-on controller. We're going to use a small DC fan. This particular one is a 12-volt DC. And then we're going to use our base Peltier plate. And we can create our own miniature version of this one, or you can buy that whole one. I think it was around $30 or so. Very inexpensive thing to have in the classroom to be able to teach these principles and to help understand the correlation between heat movement and electron movement. Pretty interesting, huh?
Jason O says digital or Bluetooth refrigerant.
That's right. None. NA would be the refrigerant here. So I was very intrigued. How many BTUs for that demo? Robert, I will pull that up because it was the largest one. The large fan was 150, and then the small one, it was fractional. I think it was like 25, so not a BTUs, but very, very small component to be able to do that also. I'll be right back. I'll bring it here with me. so we can get a closer view on it. Or actually, Jocelyn, let's go back to the camera. And this one probably brings it up closer. We'll see.
What was that one?
Yeah. How's the view on that one? That would be 3.
Okay.
Not bad?
It's good.
All right. So remember, we're just using our heatsink, and these are very detachable. So this is something that can be constructed in classroom as separate parts. And I think it was around 150 BTUs this one was actually running. And so we're going to be from our room air, drawing in heat from our space. That heat is going to be transferring through our Peltier plate into, which this one's evaporator, which is still very, very cold. And so we're going to have a smaller amount of airflow, because we're trying to keep that consistent evaporator temperature. But this one's already sweating. And so for a small amount of money, we can teach that principle of heat transfer in a nice little package unit. So highly encourage introducing that into the classroom. All right. Any questions from the audience?
I don't know what this means.
Oh, the BlackBerry is a little before your time. The BlackBerry was our first communicating device past a phone that just had buttons on it. Okay. So let's think about that transfer and think about ways that we can discuss newer forms of technology in the classroom. I wanted to bring this up. How does a solar panel operate? Because remember, this entire studio is being ran by solar panel right now. How do we produce voltage off from a solar panel? So this was just a conversation that led into an entire another exploration. A few weeks ago, we had quite a few comments from the audience that wanted to learn more about solar. So I think it's a good time for us to start diving into solar. What do we do with the solar? Let's go to our next slide and talk about this. A solar cell, looky there, it uses the same N-type and P-type semiconductors. We create layers of them, and then we add a conductor between those lines that you see on the photocell. That is just our electrical path connecting our N and P type semiconductor plates. Instead of using heat, we're going to use a different process called photovoltaic, where we're using another form of energy. Because remember, the heat, what is the heat? It's the energy source. If we use sunlight source of energy, the photovoltaic, we accomplish the exact same process. We allow the energy to create a temperature differential between the top of our panel and the bottom of our panel. And as we introduce that solar energy, we're doing the exact same process as we were doing with thermoelectric. We are exciting electrons from the P plate through the N plate. We're going to gather those electrons, going to give them a path, a wire, an electrical path, and we are going to generate electricity out of the exact same style semiconductors that we used in thermoelectricity. So it all keeps going back. It's all the same types of technology doing different types of work. And as HVAC professionals and as HVAC educators, I feel it's very important for us to be able to start discussing these topics in the classroom, because we are moving into a new generation of equipment where we're starting to see hybrid HVAC systems that use solar panels for assistance. There's even one out there from Hotspot Energy that is completely solar. It has no electrical connection whatsoever. It's been driven completely off from solar panels. And so solar and the entire semiconductor voltage creating principle is very much moving into our industry. So what do you think? That's a lot of stuff over some little bitty parts, don't you think?
Yeah.
So if anyone has any questions, I encourage you to let us know in the chat. And we definitely had some interest in learning more about semiconductors. So I think we will bring in Professor Eugene Silberstein to dive into semiconductor manufacturing and functionality and how we actually move those electrons from one type through the holes of another type to be able to move those electrons to get the voltage actually flowing. And all of these parts were available on Amazon, so they're inexpensive for the classroom, and it makes a great educational tool. Well, it's a little short this week. I thought I would have spent a little bit more time on that one. That really covers all of our principles. Any other questions or comments while we got a little bit of time? Yeah, Jason, I'm glad you enjoyed that. It was so intriguing for me to dive a little bit deeper and start understanding what these principles were. All right. Well, we appreciate everybody joining us today. Look forward to diving deeper into semiconductors and solar technologies. And we will see you all again next week on Did You Know? The ESCO HVAC Show. Bye, everybody.